I'd like to show you another way of solving a linear system that's known as linear combination. It's a different technique than substitution. I personally prefer it, but just like substitution, it's the same goal. You're trying to find the intersection point of two lines. So let me give you an example of what you might see. Okay. So these are two equations of two different lines. They are not parallel, so they're going to intersect at some point, and we want to algebraically figure out where that point is. Instead of isolating a variable and then trying to substitute it in the other equation, I like to just take these guys and combine it. Notice the negative y and the positive y will cancel, and all of a sudden I've solved for x. Once I know x, I can replace it in either the first or the second equation. Minus y is equal to 2, y is equal to negative 2. I just found the intersection of the points by combining the equations together. And I've got several examples because, like everything else, it's going to get a little bit harder. This one's going to be very similar to the one we just had. Combine them and you've got 8x is equal to 8, so x is 1. Go back to the first equation, replace x with 1. 3 plus 2y is equal to 7. 2y is equal to 4. Y is equal to 2. So when they start getting more difficult is in this example. The first two examples, if you notice, you had the opposite number of y's in each example. Here, if we added these together like they are right now, we'd have 12x and 5y. So we wouldn't have eliminated one of the variables. But I think if we just change this by multiplying the entire equation by a negative sign, we would now have 9y equals negative 27. So y equals negative 3. You can take each equation separately, and you can manipulate it any way you want, as long as you're doing the same thing to one side as the other. And then I'm going to replace this back in for y. So I'll have 6x plus 7 times negative 3 equals negative 15. 6x minus 21 equals negative 15. 6x equals 6. So x must be 1. So my intersection point is positive 1, negative 3. Two more. So again, if I add them like they are now, I'll wind up with negative 3x and positive 3y. So I've got to manipulate one or both equations if necessary to be able to do that. Now I don't want this guy up here. If I'm trying to eliminate y's, I don't want to multiply this equation by a positive 2. Then I would have 4y. So instead I'm going to multiply the entire equation by negative 2. So I get negative 4x minus 2y equals negative 26, and negative 5x plus 2y. So now I'm recopying the bottom problem. Negative 9x, the y's are eliminated. So that's why some people call this technique elimination. I call it linear combination. And x is equal to 3. I'm going to go back to my first equation. Replace x with 3. And y is 7. And then the last one I'm going to give you is the hardest one. And that is because we are going to have to manipulate both equations if we want to have success with linear combination. So I can't manipulate just one equation. We won't be able to get there. If I wanted to eliminate the y's, I could multiply this equation by 4 and this one by 5. But I'm going to try, because the x's are a little bit smaller and easier to work with, I'm going to try to eliminate the x's. And so what I'm looking for is a greatest multiple of 2 and 3, which is 6. So I'm going to multiply the first equation by 3 and the bottom equation by 2. And I'll get 6x minus 15y is equal to 30, and negative 6x plus 8y is equal to negative 15. Oh, whoops, sorry. Is equal to negative 30. My fault. Okay. So I get negative 7y is equal to 0, so that means y must equal 0. And if y is 0, 2x equals 10, x is equal to 5. Don't be nervous if you get an answer like 0. 0 is a number and it can be an intersection point. It happens to be at the point 5, 0 here. Okay.